100 million invisible predators drift through our galaxy right now. Most will never be seen. Some are heading our way. These aren't science fiction monsters. They're rogue black holes, wandering the Milky Way in complete darkness, and until recently, we had no way to prove they even existed. In 2022, astronomers finally confirmed the first one, a discovery that took nearly a decade of painstaking observation to achieve. What they found changes everything we thought we knew about what's really out there between the stars. Right now, as you're reading this, approximately 100 million black holes are moving through our galaxy. Think about that number for a moment. 100 million. Not clustered safely at the center of distant galaxies where we expect to find them, but scattered throughout the spiral arms, drifting past stars, through nebulae, across the empty voids between solar systems. Every single second, somewhere in the universe, a new stellar mass black hole is born from a dying star. They don't announce themselves. They don't emit light. They simply appear and begin their silent journey through space. Here's what makes this truly unsettling. Out of those 100 million black holes in the Milky Way, we've only managed to identify about a dozen with certainty. The rest remain completely invisible, undetectable by conventional means, known only through mathematical predictions and theoretical models. We're living in a galaxy where the vast majority of some of the most extreme objects in physics are completely hidden from view. The odds seem impossible at first. About 1 in every 1,000 stars has the potential to become a black hole. Our galaxy contains roughly 100 billion stars. Do the math, and you arrive at that staggering estimate of 100 million black holes. But these aren't evenly distributed. They don't sit in neat, predictable orbits. Some cluster near the galactic center, packed by the thousands into a single cubic parsec of space. Others have been flung outward by violent events, racing through the galaxy at speeds exceeding 1,000 kilometers per second. A few have been ejected entirely, cast out into intergalactic space where they'll wander alone for billions of years. What astronomers call a rogue black hole isn't just any black hole. It's one that travels alone, without a companion star, without an accretion disk of glowing matter to mark its position. These solitary wanderers are the hardest to find because they emit no light, no radiation, no signal whatsoever. They're defined purely by absence, by what they're not rather than what they are. And yet, despite being invisible, they're out there in enormous numbers, their gravity quietly reshaping the paths of stars and gas clouds as they pass. The first confirmed rogue black hole sits about 5,000 light-years from Earth. That's relatively close in cosmic terms, closer than the supermassive black hole at the center of our galaxy. It masses about 7 times the weight of our Sun, give or take nearly a full solar mass of uncertainty. The discovery didn't come from seeing the black hole itself. That's impossible. Instead, astronomers watched a distant star brighten and shift position over the course of 6 years as something invisible passed in front of it, bending space itself. This detection method is called gravitational microlensing, and it's the only viable technique we have for finding isolated stellar mass black holes. When a massive object passes directly between us and a background star, the foreground object's gravity acts as a lens, magnifying and distorting the light from the star behind it. Most microlensing events last a few days or weeks. This one lasted nearly a year, which told astronomers they were looking at something extraordinarily dense and dark. 2 ground-based telescopes caught the initial signal. Then the Hubble Space Telescope tracked the event with unprecedented precision from 2011 through 2017, and again in 2021 and 2022. Nearly a decade of observations to confirm a single object. Why did it take so long? Because the alternative explanations had to be systematically ruled out. Could it be a neutron star instead? A brown dwarf? A very dim white dwarf? Each possibility required careful analysis of how the background star's light changed over time. The duration of the lensing event, the way the star's position shifted, the subtle color changes in its spectrum. All of these factors had to align with the predictions for a black hole of specific mass and distance. When the final analysis was complete, there was no other explanation that fit the data. This was a lone black hole, wandering through space with no companion, no debris, nothing but pure gravitational presence. The confirmation sent ripples through the astronomical community. Not because anyone doubted black holes existed in large numbers. The theory has been solid for decades. But confirming theory with observation are two fundamentally different things. This was the first unambiguous detection, the first time astronomers could point to a specific location in the sky and say with certainty, there is a rogue black hole, and here's the evidence. Now the questions multiply. If we found one, how many more are within detection range? How many have passed through our local neighborhood in the past million years without us knowing? The Milky Way is vast, spanning 100,000 light-years from edge to edge, and our ability to detect these objects drops off rapidly with distance. We can only spot microlensing events when a black hole happens to pass almost exactly between us and a background star, a geometric coincidence that's extraordinarily rare. Most black holes will never trigger such an event from our vantage point. This is where the numbers become truly staggering. NASA's upcoming Nancy Grace Roman Space Telescope, scheduled to launch in 2027, is expected to detect several thousand microlensing events. Many of those will be black holes. The Gaia mission, which has been precisely measuring the positions of over 1 billion stars, will release lensing data in 2025 that should contain evidence for many more stellar mass wanderers. We're on the verge of transforming rogue black holes from rare curiosities into a well-characterized population. Within a few years, we'll have statistical samples large enough to map their distribution, measure their velocities, and understand their role in galactic evolution. But here's what keeps astronomers up at night. Even with these next-generation instruments, we'll still only be scratching the surface. The Roman telescope might find a few thousand black holes. That's less than 1% of the estimated population. The overwhelming majority will remain invisible, their positions unknown, their trajectories unmapped. We'll have better statistics, more data points, refined models. We still won't know where most of them are. Some of these black holes aren't just wandering aimlessly. They're moving with purpose, carved trajectories determined by violent events in their past. When a massive star explodes as a supernova, the explosion is rarely perfectly symmetrical. Asymmetries in how the star's outer layers are blasted away create an unbalanced gravitational tug on the collapsing core. The result is what astronomers call a natal kick, where the newborn black hole is flung away from its birthplace like a cosmic cannonball. The fastest ones reach velocities exceeding 1,000 kilometers per second, fast enough to escape the gravitational pull of their parent star clusters entirely. These aren't gentle drifts through space. A black hole moving at those speeds crosses the distance from Earth to the Moon in less than 7 minutes. In a single year, it travels more than 30 trillion kilometers. Over millions of years, these objects can traverse the entire galaxy, their paths determined by the chaotic final moments of their parent stars' deaths. Some will eventually slow down, their velocity gradually sapped by gravitational interactions with other objects. Others will maintain their speed indefinitely, permanent wanderers that will never be gravitationally bound to any system again. The violence of their births reveals something profound about stellar death. When we imagine a supernova, we often picture a symmetric explosion, a star's outer layers expanding outward in a perfect sphere. Reality is messier. The core collapse happens in less than a second, but the shock wave that tears the star apart takes hours to propagate through its outer layers. During that time, instabilities develop. Convection cells the size of planets churn through the exploding star. Neutrinos, streaming outward by the trillions, carry away energy unevenly. By the time the explosion is complete, the geometry is chaotic, asymmetric, unpredictable. That asymmetry is precisely what creates the kick. It's a gravitational tug-of-war where the expelled material on one side of the collapsing core pulls slightly harder than the material on the other side. The difference might seem tiny when you're talking about forces at stellar scales, but when you compress that force onto an object the size of a city containing multiple times the sun's mass, the acceleration becomes enormous. The black hole is born moving, often at velocities high enough to escape its birthplace entirely. Not all rogue black holes come from natal kicks, though. Some have far more dramatic origin stories. When black holes merge, they don't simply combine quietly. The collision generates gravitational waves, ripples in spacetime itself that carry tremendous energy. Those waves don't radiate equally in all directions. If the two merging black holes have different masses or spins, the gravitational wave emission becomes asymmetric. The result is recoil, a kick delivered by the universe's most powerful force. In extreme cases, with the right combination of masses and spins, that recoil can reach speeds up to 4,000 kilometers per second. 4,000 kilometers per second. That's fast enough to escape any known galaxy. A supermassive black hole kicked at that velocity wouldn't just become a rogue. It would be ejected into intergalactic space entirely, doomed to wander the cosmic voids between galaxies for eternity. The physics behind these superkicks reveals something extraordinary about how spacetime itself can be weaponized. When two black holes spiral toward each other in their final moments before merger, they're not just falling together. They're stirring spacetime around them like massive spoons in cosmic honey. Each black hole drags the fabric of space along as it orbits, creating gravitational waves that ripple outward at the speed of light. If those black holes have identical masses and spins perfectly aligned, the waves radiate symmetrically. The forces balance out. But change even one variable, make one black hole heavier or spin it at a different angle, and that symmetry breaks. The gravitational waves become lopsided. More energy flows in one direction than the others. When the merger finally happens, when those two black holes become one, conservation of momentum demands payment. All that asymmetric wave energy has to come from somewhere. It comes from the newly formed black hole's velocity. The merged object recoils, kicked by its own gravitational radiation like a cannon firing itself backward. Gravitational wave observatories have actually caught this happening. In 2019, detectors picked up a signal designated GW190412. Two black holes merged, one significantly more massive than the other. Analysis of the signal revealed something remarkable. The resulting black hole was kicked at over 50 kilometers per second, fast enough to escape the globular cluster where it formed. That's just one event we happen to detect. Similar mergers are happening throughout the universe constantly, each one potentially creating a new rogue. The most extreme kicks require a specific configuration. The black holes need to have roughly similar masses, both spinning rapidly, and those spins need to be oriented in the orbital plane, pointing sideways rather than up or down. Get all those factors aligned just right, and the recoil can hit those velocities of 4,000 kilometers per second. At that speed, you're not creating a galactic rogue. You're ejecting a black hole from the galaxy entirely, sending it out into intergalactic space where it will drift alone for the rest of cosmic time. There's a third way to make a rogue black hole, and it's probably the most common mechanism for the supermassive ones. It requires 3 black holes, a situation that sounds unlikely until you remember that galaxies merge constantly throughout cosmic history. Picture 2 galaxies colliding. Each galaxy has a supermassive black hole at its center, millions or billions of times the Sun's mass. As the galaxies merge, their central black holes sink toward the center of the newly combined galaxy. They form a binary pair, orbiting each other in an ever-tightening spiral. Now add a third galaxy to the collision. It happens more often than you'd think. Galaxy groups and clusters are messy places where multiple galaxies can interact simultaneously. When that third galaxy's central black hole arrives, it encounters the existing binary. 3 bodies orbiting under mutual gravitational attraction create one of physics' most infamous problems. The 3-body problem has no general solution. The system is chaotic, unpredictable, fundamentally unstable. Something has to give. Usually, it's the lightest black hole that gets ejected. The 2 heavier ones transfer some of their orbital energy to the third, flinging it away at tremendous velocity. Simulations show these 3-body interactions can easily produce ejection speeds of several thousand kilometers per second. The Milky Way's own history likely created rogues this way. Our galaxy has absorbed dozens of smaller galaxies over billions of years. Each of those small galaxies probably had its own central black hole, ranging from thousands to millions of solar masses. When they merged with the Milky Way, their black holes sank toward our galactic center, where Sagittarius A*, our supermassive black hole, was waiting. Some of those intruders would have merged with Sagittarius A*, adding their mass to it. But others might have had close encounters that flung them back out, sending them on long arcs through the galaxy's halo. Calculations suggest hundreds of these intermediate mass black holes could be wandering the Milky Way's outskirts right now, each one containing anywhere from 1,000 to 100,000 solar masses. Finding these rogues should be impossible. They emit no light, no radiation, nothing that would mark their location. For decades, they remained purely theoretical objects, predicted to exist but never observed. Then astronomers got creative about using gravity itself as a detection tool. The technique is called gravitational microlensing, and it exploits a consequence of Einstein's general relativity. Mass warps spacetime around it. Light traveling through that warped space follows curved paths. If a massive object passes between us and a distant star, the object's gravity bends the star's light, acting like a natural magnifying glass. For most objects, this lensing effect is brief. A normal star might lens a background star for a few days or weeks as it passes in front. But black holes are different. They're incredibly dense, packing enormous mass into tiny volumes. Their gravitational lensing signature is distinct, unmistakable, and crucially, it lasts longer than a normal star's would. In 2011, 2 separate sky surveys detected a distant star beginning to brighten. Nothing unusual at first. Microlensing events happen regularly. Astronomers observe thousands of them. But as weeks turned to months and the event continued, suspicion grew. The duration suggested the lensing object had to be extremely massive relative to its size. The Hubble Space Telescope swung into action, making precise measurements of the star's position over 6 years. Not just its brightness, but its actual location on the sky. As the invisible object passed in front, its gravity didn't just magnify the star's light. It shifted the star's apparent position, deflecting the light's path through space. By 2022, after more than a decade of observations, the conclusion was inescapable. The lensing object was a black hole, roughly 7 times the Sun's mass, located about 5,000 light-years away. No companion star, no accretion disk, no surrounding nebula. Just a lone black hole drifting through space, its presence betrayed only by the warping of spacetime around it. This was the first confirmed rogue black hole ever detected. Not the first suspected one. Not the first candidate. The first time astronomers could point to a specific location in space and say with certainty that an isolated, wandering black hole exists there. The discovery validated decades of theoretical predictions and proved that microlensing could reveal these invisible objects. But it also raised an uncomfortable question. If it took 6 years of Hubble observations to confirm just one rogue black hole, how many others are out there that we simply haven't found yet? Estimates suggest 100 million stellar mass black holes exist in the Milky Way alone. We've confirmed the existence of about a dozen. The math is sobering. We found roughly 1/10,000,000th of the predicted population. The galaxy could be thick with these objects, and we'd have no idea because they're fundamentally invisible unless they happen to pass directly between us and a background star we're monitoring. That gap between prediction and observation is about to narrow dramatically. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will conduct microlensing surveys far more comprehensive than anything attempted before. Where Hubble might track hundreds of stars looking for lensing events, Roman will monitor millions simultaneously. Projections suggest Roman could detect thousands of black hole lensing events during its mission. Each one would provide precise measurements of mass, distance, and velocity. For the first time, astronomers would have statistical data on the rogue black hole population, revealing not just that they exist but how many there are, where they cluster, how fast they typically move. The Gaia spacecraft, currently mapping the positions and motions of over 1 billion stars in the Milky Way, will contribute too. Its 2025 data release is expected to contain evidence of numerous microlensing events, many likely caused by black holes. By combining Roman's targeted searches with Gaia's wide-field monitoring, astronomers anticipate finally characterizing this hidden population. But supermassive rogues require different detection strategies. They're rarer, more distant, and their effects on their surroundings can be more dramatic. When astronomers want to find a wandering supermassive black hole, they look for the violence it leaves in its wake. In 2024, astronomers detected something extraordinary through a phenomenon called a tidal disruption event. When a star wanders too close to a black hole, tidal forces tear it apart in a process known as spaghettification. The star gets stretched vertically while being compressed horizontally, like cosmic taffy being pulled apart by gravity's relentless grip. Most of the stellar material forms an accretion disk around the black hole, heating to millions of degrees and blazing across multiple wavelengths of light. These events are rare, occurring perhaps once every 10,000 to 100,000 years in any given galaxy. About 100 have been observed so far. But the tidal disruption event designated at 2024 TVD was different. It happened in the wrong place. Supermassive black holes sit at the centers of galaxies. That's where they belong, anchored by billions of years of gravitational accumulation. When a tidal disruption event occurs, the flare appears at the galaxy's nucleus. Astronomers see the bright point of light coinciding precisely with the galactic center, confirming the black hole's expected location. At 2024 TVD's flare appeared offset from its galaxy center. Not by a small amount, either. Hubble observations showed the tidal disruption occurred about 2,600 light-years away from where the galaxy's central supermassive black hole should be. That's a substantial displacement, roughly equivalent to the distance between our Sun and many nearby stars. The Chandra X-ray Observatory and the Very Large Array Radio Telescope confirmed what Hubble revealed. The black hole consuming that unfortunate star wasn't sitting at the galactic nucleus. It was wandering through the galaxy's bulge, a rogue supermassive black hole displaced from its throne. Mass estimates put this wandering black hole at roughly 1 million times the Sun's mass. Not particularly large by supermassive standards, but still an object whose gravity dominates everything in its vicinity. And here's what made the discovery even more remarkable. When astronomers examined the galaxy's actual center, they found another supermassive black hole, this one weighing 100 million solar masses. One galaxy. Two supermassive black holes. The smaller one displaced, the larger one occupying the central position. This configuration tells a story about galactic violence, about mergers and gravitational warfare that played out over millions of years. How does a supermassive black hole get kicked out of its galaxy's center? The mechanics differ dramatically from the stellar mass rogues created by supernova kicks. You can't asymmetrically explode a million solar mass black hole. The forces required operate on an entirely different scale. The most likely explanation involves gravitational wave recoil. When two supermassive black holes orbit each other, they emit gravitational waves, ripples in spacetime itself that carry energy away from the system. As they spiral inward, the gravitational wave emission intensifies. The final moments before merger release tremendous energy in the form of these waves. If that emission isn't perfectly symmetrical, if the gravitational waves radiate preferentially in one direction, the merged black hole experiences recoil. Newton's third law applies even here. The asymmetric emission pushes the black hole in the opposite direction, imparting velocity that can reach several thousand kilometers per second. Simulations show that certain configurations of mass and spin can generate kicks exceeding 4,000 kilometers per second. That's faster than the escape velocity of any known galaxy. A supermassive black hole receiving such a kick would leave its galaxy entirely, ejected into intergalactic space with no hope of return. But not all kicks are that extreme. Most gravitational wave recoil events produce velocities of hundreds to low thousands of kilometers per second. Enough to displace a black hole from the galactic center, but not enough to expel it completely. The black hole remains gravitationally bound to its galaxy, oscillating through the galactic bulge in a complex orbit that takes millions of years to complete. At 2024 TVD represents exactly this scenario. The black hole is displaced but not ejected. It's wandering but not lost. Eventually, over timescales spanning tens or hundreds of millions of years, dynamical friction will slow its motion. Gas and stars will gradually sap its orbital energy. It will spiral inward, returning to the galactic center where it might merge with the larger central black hole already residing there. But that future merger lies in the distant future. Right now, we're witnessing the aftermath of a previous collision, seeing a galaxy still settling from gravitational upheaval that occurred long ago. The discovery raised immediate questions. If one galaxy harbors a displaced supermassive black hole, how many others do? Are wandering supermassive black holes common or rare? Have we simply been looking in the wrong places, assuming all supermassive black holes sit obediently at galactic centers? Research into dwarf galaxies suggested the answer might be unsettling. A study examining over 3,000 dwarf galaxies found that about 62% showed signs of active black hole accretion offset from their optical centers. Not slightly offset. Substantially displaced, by hundreds or thousands of light-years. One particularly compelling case involved a dwarf galaxy located 230 million light-years away. The black hole wasn't just offset from the center. It was actively launching radio jets, visible evidence of ongoing accretion. This wasn't a dormant relic gradually settling back toward the nucleus. This was an active, feeding black hole wandering through its galaxy's outskirts. The prevalence of offset black holes in dwarf galaxies suggests something profound. The traditional picture of galactic structure, with supermassive black holes anchored permanently at the center, may be an idealized version of reality. The actual universe appears messier, populated by galaxies where black holes wander, displaced by mergers, gravitational interactions, and the chaotic dynamics of galactic evolution. This realization carries implications for our understanding of how supermassive black holes grow. If black holes can accrete material while displaced from galactic centers, if they can feed and gain mass while wandering through their host galaxies, then the pathways to supermassive black hole growth are more varied than previously thought. It might also explain how supermassive black holes grew so rapidly in the early universe. Observations reveal quasars powered by billion solar mass black holes existing when the universe was less than 1 billion years old. How did these objects grow so massive so quickly? If black holes can feed efficiently even while displaced from optimal galactic positions, if wandering doesn't necessarily mean starvation, then multiple growth channels exist beyond simple accretion at the galactic nucleus. But the most dramatic example of a displaced supermassive black hole comes from a galaxy designated 3C186, located 8 billion light-years away. Hubble observations revealed a quasar, the bright signature of an actively feeding supermassive black hole, offset from the galaxy's center by 35,000 light-years. 35,000 light-years. That's more than the distance from our Sun to the Milky Way center. This black hole wasn't slightly displaced. It was flung across a substantial fraction of its entire galaxy. Spectroscopic analysis revealed something else. The black hole was moving at roughly 2,000 kilometers per second relative to its host galaxy. At that speed, it would take about 24 million years for the black hole to complete one oscillation through the galaxy, assuming it remains bound at all. Some estimates suggest 3C186 black hole might have received enough velocity to escape its galaxy entirely. If true, we're witnessing a supermassive black hole in the process of leaving home, ejected by gravitational wave recoil and headed into the void between galaxies. What created such a violent kick? The most plausible scenario involves a merger between two supermassive black holes with particular mass ratios and spin configurations. Computer simulations can reproduce kicks of this magnitude, but only under specific conditions. The black holes must have been spinning rapidly, their spins must have been misaligned with their orbital plane, and the mass ratio must fall within certain ranges. These requirements aren't particularly rare on cosmic scales. Galaxy mergers happen constantly throughout the universe. Many of those galaxies harbor supermassive black holes. When galaxies merge, their black holes eventually merge too, and a fraction of those mergers will produce the right conditions for extreme gravitational wave recoil. Estimates suggest hundreds of rogue supermassive black holes might wander the Milky Way's outskirts. Not stellar mass rogues, but intermediate mass and supermassive black holes ejected from dwarf galaxies during the Milky Way's assembly billions of years ago. Each one represents a relic from the galaxy-building era, a black hole displaced during mergers and kicked into the galactic halo where it now drifts in the darkness. These objects would be extraordinarily difficult to detect. They're not accreting material in the sparse halo environment. They produce no light, no jets, no observable signature except their gravitational influence. Unless one passes directly in front of a background object we're monitoring, or unless it encounters gas or stars that it can consume, it remains invisible. But there's another way wandering supermassive black holes can reveal themselves. One that's both spectacular and completely unexpected. They can create stars. In 2023, astronomers spotted something that shouldn't exist. A streak of light stretching 200,000 light-years through intergalactic space. Not a galaxy. Not a jet. A trail of newborn stars following a black hole. The black hole itself weighs 20 million solar masses. It's racing through the void at 1,600 kilometers per second, plowing through tenuous gas clouds like a cosmic icebreaker. As it moves, it compresses gas in its wake. That compression triggers star formation. The result is a luminous trail of hot blue stars marking the black hole's path through space like contrails behind an aircraft. The trail's brightness reaches nearly half that of the black hole's host galaxy. Think about that. A single object, invisible and compact, creating a stellar wake so bright it rivals an entire galaxy's worth of stars. The phenomenon was discovered almost by accident during routine observations, appearing as an unusual linear feature that didn't match any known astronomical object. Initial analysis suggested the trail was approximately 39 million years old. Which means we're witnessing a process that began when Earth was home to early primates. The black hole has been creating stars continuously throughout that entire period, transforming empty space into stellar nurseries as it travels. How does this work? The physics is surprisingly straightforward. As the black hole moves through intergalactic medium, the extremely tenuous gas that fills the space between galaxies, it creates a bow shock. Similar to how a boat creates a wake in water. But instead of water, this wake consists of compressed hydrogen gas. The compression raises the gas density above the threshold needed for gravitational collapse. Stars begin forming in the compressed regions. The black hole continues moving. The newly formed stars remain behind, creating a trail that traces the black hole's path. The discovery raises immediate questions. If one rogue supermassive black hole can create such spectacular effects, how many others are doing the same thing undetected? The intergalactic medium is vast and mostly empty, but it's not completely devoid of material. Any supermassive black hole traveling through it at high velocity should theoretically produce similar compression effects. Astronomers estimate hundreds of rogue supermassive black holes might exist in the Milky Way's halo alone, ejected from dwarf galaxies during the galaxy's formation billions of years ago. Most wouldn't be creating visible star trails because they're moving through regions too sparse to support star formation. But some fraction, those traveling through slightly denser regions or those with particularly high velocities, might be creating trails we simply haven't noticed yet. The search is now on. Telescopes are being programmed to look for similar linear features in deep space images. The characteristic signature is specific enough to distinguish from other phenomena. A narrow trail. Consistent width. Blue coloration indicating young massive stars. Alignment suggesting directional motion rather than random distribution. But here's where things get more complicated. Not all rogue black holes announce their presence so dramatically. The vast majority remain completely invisible, detectable only through their gravitational influence. Which brings us to the question that should concern us most. What happens if one passes through our neighborhood? The odds are reassuringly low. Astrophysicists calculate the probability of a stellar mass rogue black hole approaching close enough to significantly disrupt our solar system at roughly 1 in a few hundred million over the next billion years. Those aren't terrible odds. But they're not zero either. Distance determines everything. A black hole passing a few hundred light years away would have absolutely no effect. We wouldn't notice it unless it happened to pass in front of a star we were monitoring. But as the distance decreases, effects begin to accumulate. At 100 astronomical units, just beyond Pluto's orbit, a stellar mass black hole would start affecting the outer planets. Uranus and Neptune might experience orbital perturbations. Pluto's orbit would definitely change. But Earth, safely nestled in the inner solar system, would remain largely unaffected. The real danger begins if the black hole crosses into the region between Uranus and Saturn. At that range, Earth's orbit starts feeling gravitational tugs. Nothing catastrophic immediately. Just gradual changes that accumulate over thousands of years. Seasons might lengthen or shorten. Climate patterns would shift as Earth's orbital parameters changed. If the black hole passed within Saturn's orbit, we're looking at serious problems. The gravitational influence would likely push Earth outside the habitable zone where liquid water can exist. Temperatures would drop. Oceans might freeze. Or depending on orbital mechanics, Earth might move closer to the Sun, experiencing runaway greenhouse heating. Within Jupiter's orbit, tidal effects become dominant. Earth wouldn't just orbit the Sun anymore. It would begin orbiting the black hole, or more accurately, both Earth and the Sun would orbit their common center of mass with the black hole. The planet's geology would respond violently to changing tidal forces. Massive earthquakes, volcanic eruptions, complete reshaping of the surface. And if a black hole passed between Earth and Mars, the planet becomes uninhabitable. Period. Tidal heating would melt the crust. Oceans would boil away. The atmosphere would be stripped. Earth would be resurfaced by magma, transformed into a molten ball orbiting an invisible gravitational well. These scenarios sound apocalyptic. But remember the probabilities. Space is incomprehensibly vast. Black holes are rare compared to stars. The Milky Way contains an estimated 100 million stellar mass black holes among hundreds of billions of stars. That's roughly one black hole per 1,000 stars. And most of those black holes are concentrated toward the galactic center, not scattered uniformly throughout the disk. Our solar system orbits in the galactic suburbs, about 26,000 light-years from the center. Black hole density is lower here. The nearest known stellar mass black hole sits about 1,500 light-years away, not exactly close. And it's not moving toward us. The more likely scenario involves the Oort cloud, a spherical shell of comets surrounding our solar system extending roughly 1 light-year from the Sun. If a rogue black hole passed through the Oort cloud, its gravity would disturb countless comets, potentially sending them on trajectories toward the inner solar system. Earth would experience a prolonged period of increased comet impacts. Dangerous, certainly. Extinction level if enough large comets struck. But the probability of even this scenario is estimated at about 1 in a quadrillion. Still, the mere possibility reveals something important. Our cosmic safety isn't guaranteed by physics. It's maintained by probability and distance. We're safe because space's big and dangerous objects are relatively rare, not because we're protected by any fundamental law. Detection becomes crucial. If we can identify rogue black holes in advance, if we can map their trajectories and predict close approaches, we gain time. Time to prepare. Time to potentially deflect dangerous objects. Time to understand what we're dealing with. That's where the next generation of telescopes comes in. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will revolutionize our ability to detect isolated black holes through gravitational microlensing. The mission's wide field of view and extreme sensitivity will allow it to monitor millions of stars simultaneously, watching for the telltale brightening that occurs when a massive object passes in front of them. Current estimates suggest Roman will detect thousands of microlensing events during its operational lifetime. Many will be caused by normal stars. But a significant fraction should be black holes. For the first time, we'll have a comprehensive census of stellar mass black holes in our galactic neighborhood. The European Space Agency's Gaia mission is already contributing. Gaia measures the positions and motions of billions of stars with unprecedented precision. In 2025, astronomers will release a new data set containing gravitational lensing detections from Gaia's observations. That data is expected to reveal additional rogue black holes that have passed in front of stars Gaia monitors. These efforts will transform black holes from theoretical objects we occasionally glimpse to a well-characterized population we can study systematically. We'll learn their typical velocities, their distribution throughout the galaxy, their mass spectrum. We'll understand whether current theoretical models accurately predict their numbers or whether we're missing something fundamental. But detection is just the beginning. The real scientific treasure lies in what these wandering black holes tell us about galactic evolution, stellar death, and the violent processes that shaped our cosmic neighborhood. Each rogue carries a history, the circumstances of its birth, the kick it received, the path it's traveled, the environments it's passed through. Some wandering black holes might harbor planetary systems, worlds orbiting invisible suns in permanent darkness. The planets would receive no light, only gravitational influence and perhaps tidal heating. Life on such worlds seems impossible by conventional standards. But the universe has surprised us before. Others might act as cosmic vacuum cleaners, slowly accumulating material as they drift through molecular clouds. Given enough time, some might even accumulate enough mass to become intermediate mass black holes, filling the gap between stellar mass and supermassive varieties. And all of them, every single wandering black hole, represents a data point in the largest physics experiment ever conducted. An experiment running for billions of years across an entire galaxy, testing our understanding of gravity, stellar evolution, and the fundamental nature of space-time itself. The invisible wanderers are out there right now, moving through the darkness, creating stars in their wakes, warping space-time, carrying the secrets of their violent births across light years of empty space. We're just beginning to find them. And that's what makes this moment in astronomy so extraordinary. For the first time in human history, we're not just theorizing about these objects. We're actually finding them. Consider what happened in early 2024. Astronomers using Hubble identified a wandering supermassive black hole through a tidal disruption event designated at 2024 TBD. A star wandered too close. The black hole's gravity shredded it. The resulting flare of X-rays and optical light revealed something unexpected. The black hole wasn't at the galaxy's center. It was offset, displaced by 2,600 light-years from where it should be. And here's what makes this discovery remarkable: that galaxy has another supermassive black hole sitting exactly where you'd expect, right at the center, weighing about 100 million solar masses. Two supermassive black holes. Same galaxy. One wandering. Out of roughly 100 tidal disruption events detected so far, this is the first offset case confirmed. Which raises an immediate question: is this rare, or have we just been looking in the wrong places? The data suggests the latter. When astronomers surveyed over 3,000 dwarf galaxies using the MONDIS survey, they found something stunning. About 628 showed signs of active black hole feeding, and 62% of those appeared offset from their galactic centers. 62%. These aren't exceptions. They might be the norm, at least for smaller galaxies. The traditional picture of black holes sitting peacefully at galactic centers like cosmic monarchs begins to look less like reality and more like an idealized textbook illustration. But dwarf galaxies are one thing. What about wandering black holes at the edges of major galaxies like our own? Theory predicts they're out there. Hundreds of intermediate mass black holes, each containing between 1,000 and 100,000 solar masses, should be drifting through the Milky Way's outskirts. These aren't stellar mass rogues born from single stars. They're relics from the galaxy's formation. Billions of years ago, when the Milky Way was assembling itself from smaller proto-galaxies, each of those dwarf galaxies likely harbored a central black hole. As they merged, their black holes merged too. And when two black holes merge, they emit gravitational waves. Those waves carry momentum. If the emission isn't perfectly symmetrical, the merged black hole receives a kick. Sometimes a gentle nudge. Sometimes a violent shove exceeding the escape velocity of the host galaxy entirely. The calculations suggest about 12 rogue supermassive black holes might be wandering the Milky Way's halo right now. Cosmic fossils from our galaxy's violent youth. They've been traveling for billions of years, silent witnesses to galactic evolution, carrying information about conditions in the early universe. Finding them would be transformative. But there's a problem. These objects emit no light. They're not actively feeding. They're just moving through near-empty space, invisible, detectable only through their gravitational influence. Which brings us back to the detection methods that will define the next decade of black hole astronomy. Gravitational microlensing remains our most powerful tool. When a massive object passes between us and a distant star, it bends spacetime. The star's light follows that curved geometry, temporarily brightening as the lens magnifies it. The effect lasts anywhere from days to over a year depending on the lensing object's mass and velocity. The first confirmed isolated stellar mass black hole, discovered in 2022, was detected exactly this way. Hubble monitored a background star from 2011 to 2022, watching its brightness fluctuate as an invisible object passed in front. The microlensing event lasted long enough and showed characteristics that could only be explained by a black hole about 7.1 solar masses, located roughly 5,000 light-years away. One detection. 11 years of observations. That's the challenge. But it's also why the Roman Space Telescope represents such a leap forward. Its wide field of view will monitor millions of stars simultaneously. Current ground-based microlensing surveys have detected about 30,000 events total over decades. Roman is expected to find several thousand in just its primary mission. Many will be caused by normal stars or planets. But a significant fraction should be black holes. For the first time, we'll have enough detections to study them statistically, to understand their velocity distribution, their typical masses, how many were born with kicks versus how many formed more quietly. The 2025 Gaia data release will contribute too. Gaia measures stellar positions with microarcsecond precision. When a black hole passes near a star, it doesn't just brighten it through lensing. It also shifts the star's apparent position. Gaia's astrometric measurements can detect these tiny deflections, revealing black holes through their gravitational fingerprints alone. These technologies will find stellar mass rogues. But what about the intermediate mass and supermassive wanderers? That's where gravitational waves enter the picture. When LIGO detected GW190521 in 2019, the signal revealed two black holes merging, one 85 solar masses, the other 65. The resulting black hole weighed 142 solar masses. Firmly in the intermediate mass range. And crucially, the merger wasn't symmetrical. The final black hole received a kick of about 50 kilometers per second. Not fast enough to escape a galaxy, but fast enough to be displaced from its birth site. Fast enough to become a wanderer if it formed in a globular cluster with relatively low escape velocity. Future gravitational wave observatories will detect these events routinely. LISA, the space-based detector planned for the 2030s, will observe supermassive black hole mergers across cosmic time. Each merger produces a kick. Each kick potentially creates a wanderer. By studying the statistics of these recoils, we'll understand how common displaced supermassive black holes really are. Suns should still be orbiting within their host galaxies, gradually sinking back toward the center through dynamical friction. Others might have escaped entirely, becoming truly intergalactic wanderers moving through the void between galaxies. Imagine that. A million solar mass black hole drifting through intergalactic space. No stars nearby. No gas to accrete. Just darkness and the faint microwave background radiation left over from the Big Bang. How long would such an object wander? Trillions of years, potentially. Long after the stars have burned out. Long after galaxies have merged into enormous elliptical systems. These wanderers would remain, invisible monuments to ancient violence. But not all wanderers are silent. Remember the runaway black hole creating a 200,000 light-year trail of stars? That object is actively interacting with its environment. As it plows through intergalactic gas at roughly 1,600 kilometers per second, it compresses material ahead of it. The compression triggers star formation. Hot blue stars mark its path like breadcrumbs. The trail is estimated to be about 39 million years old, which means we're seeing the black hole's trajectory frozen in time. The stars it created millions of years ago are still shining, revealing where it's been even as the black hole itself continues racing forward. This phenomenon might be more common than single detections suggest. Astronomers are now searching archival data for similar features. Long, narrow trails of star formation that don't match conventional patterns. Each one could mark another wandering black hole, another cosmic refugee from a galactic merger billions of years ago. And here's what's fascinating about this. These wanderers aren't just passive objects moving through space. They're actively shaping their environments, creating stars, potentially influencing the distribution of matter on large scales. They're participants in cosmic evolution, not just observers. What happens when one of these intermediate mass wanderers encounters a dwarf galaxy? Does it capture gas and become active again? Does it merge with the dwarf's central black hole, growing larger? Or does it pass through, creating chaos but moving on? We don't know yet. But we're about to find out. Because as detection capabilities improve, as surveys become more sensitive, as gravitational wave observatories come online, we'll catch these interactions in progress. We'll watch black holes that have wandered for billions of years finally encounter new environments. We'll see what happens when invisible objects with immense gravity meet matter that can't escape. The universe has been running this experiment for 13 billion years. We're just now developing instruments sensitive enough to observe the results. And what we're finding suggests the cosmos is far more dynamic, far more violent, far more interesting than the static picture we once imagined. Every galaxy has a history written in its wandering black holes. Every merger leaves signatures. Every kick sends an object on a journey that might never end. The invisible wanderers are everywhere, moving through darkness, carrying their stories across light years and eons. We're learning to read those stories now. And the implications extend far beyond academic curiosity. Understanding wandering black holes matters for predicting the future of our own galaxy. The Milky Way is on a collision course with Andromeda. In about 4 billion years, these galaxies will merge. When that happens, their central supermassive black holes will eventually sink toward each other, orbit, and merge. The resulting gravitational wave recoil could kick the merged black hole completely out of the newly formed galaxy. Our descendants, if they still exist, might witness their galactic center going dark. The engine that powered quasar activity, that regulated star formation, that shaped the structure of the galaxy for billions of years, simply gone. Ejected into intergalactic space by forces they can only watch helplessly. But there's something even more unsettling to consider. Right now, as you're reading this, rogue black holes are moving through our galaxy. Hundreds of them. Maybe thousands. Most are stellar mass objects, 7 to 20 times the Sun's mass, kicked out during supernova explosions. They're invisible. They emit no light. They're detectable only through gravitational effects on nearby objects or through microlensing events that last months and require incredible observational precision to catch. How close is the nearest one? We don't know. Could be hundreds of light years away. Could be closer. The first confirmed isolated stellar mass black hole was found just 5,000 light years from Earth. That's practically next door on galactic scales. And it took 6 years of Hubble observations to confirm it was actually there. Think about that for a moment. An object 7 times the Sun's mass, close enough that light from it would take only 5,000 years to reach us, and we only confirmed its existence in 2022. How many others are out there that we haven't found yet? The odds of one passing close to our solar system are astronomically low. Astrophysicists calculate the chances of a stellar mass rogue black hole coming close enough to directly disrupt our solar system at roughly 1 in a few hundred million over the next billion years. But low probability isn't the same as impossible. And when you're dealing with timescales of billions of years, even unlikely events become inevitable given enough time. What would actually happen if one did approach? The effects would depend entirely on how close it came. If it passed 100 astronomical units out, just beyond Pluto's orbit, it might alter the trajectories of the outer planets slightly. Earth probably wouldn't notice much. But if it crossed inside Saturn's orbit, things get serious. We'd likely be pushed outside the habitable zone. Liquid water couldn't exist. The delicate balance that makes Earth livable would shatter. And if it passed between Mars and Earth, the planet would be resurfaced. Tidal forces would heat the interior into magma. Oceans would evaporate. The atmosphere would be stripped away. Life would end. Not through direct collision, just through gravitational interaction with an object that doesn't even emit light. The more probable danger isn't the black hole itself but what it would do to the Oort cloud. That vast sphere of comets surrounding our solar system, stretching halfway to the nearest star. A passing black hole would gravitationally stir that cloud, sending thousands of comets cascading into the inner solar system. Some would impact Earth. The dinosaurs died from a single asteroid. Imagine dozens or hundreds arriving over centuries. But even this scenario has odds of only about 1 in a quadrillion. The universe isn't trying to kill us with rogue black holes. It's just indifferent. These objects exist. They move through space following the laws of gravity. Sometimes they pass through regions where matter exists. Sometimes they don't. The cosmos doesn't care either way. What we're really confronting here is the scale of cosmic violence. Black holes aren't gentle. They're not stable. They're not peacefully sitting at galactic centers maintaining order. They're products of catastrophic events. They're shaped by explosions, collisions, mergers. They're kicked, ejected, flung across space by forces so immense they warp spacetime itself. And yet they're also builders. The wandering black hole creating a 200,000 light-year trail of stars isn't destroying. It's creating. Compressing gas. Triggering star formation. Leaving behind stellar nurseries that will continue forming stars long after the black hole has moved on. Destruction and creation aren't opposites in the universe. They're the same process viewed from different angles. Every supernova that kicks a black hole into wandering also enriches the galaxy with heavy elements that make planets and life possible. Every galactic merger that ejects a supermassive black hole also triggers massive bursts of star formation. The violence isn't random chaos. It's how the universe builds structure, how it recycles matter, how it evolves over time. We're learning to see this now because our instruments are finally sensitive enough. The Nancy Grace Roman Space Telescope, launching in 2027, will detect thousands of microlensing events. Many will be black holes. We'll map their distribution across the galaxy. We'll understand their velocities, their masses, their trajectories. In 2025, the Gaia spacecraft will release lensing data containing evidence for dozens or hundreds more stellar mass wanderers. Each detection adds another piece to the puzzle. Each wanderer tells us something about galactic evolution, about supernova physics, about the hidden architecture of the cosmos. And gravitational wave observatories are just getting started. LIGO and Virgo have detected dozens of black hole mergers. Each merger creates a kick. Some of those remnants are wandering now, invisible but real, carrying the memory of their violent births through space. Future detectors will be more sensitive. They'll catch mergers farther away, involving more massive black holes. They'll measure the kicks directly from gravitational wave signatures. We'll watch black holes being born and simultaneously ejected, all from the comfort of Earth-based observatories. The invisible is becoming visible. Not through light, but through gravity, through the bending of spacetime, through effects on surrounding matter. We're developing new senses, new ways of perceiving reality. And what we're finding is that the universe contains far more dark, violent, wandering objects than we ever imagined. But here's what keeps me up at night. We've only scratched the surface. Every detection method we have is biased towards certain types of events. Microlensing requires perfect alignment. Tidal disruption events require the black hole to encounter a star. Gravitational waves require mergers. How many wanderers are out there that don't trigger any of these signatures? How many are moving through truly empty regions of space, never interacting with anything, forever invisible? We estimate 100 million stellar mass black holes in the Milky Way alone. We've confirmed maybe a few dozen. The ratio is staggering. We're missing 99.99% of them. And those are just stellar mass objects. The intermediate mass wanderers, the supermassive refugees from ancient mergers, those are even harder to find. We've got tantalizing hints. Offset active galactic nuclei. Star-forming trails. But confirmed detections? A handful at best. The universe is full of invisible monsters, and we're only now learning how to hunt them. Each one we find rewrites what we thought we knew. Each discovery reveals new questions. Why do some black holes get kicked at thousands of kilometers per second while others barely move? What determines whether a merger produces a wanderer or a settled remnant? How do wandering supermassive black holes affect galaxy evolution over billions of years? We don't have complete answers yet, but we're getting there. One detection at a time. One observation at a time. Building a picture of a cosmos far stranger and more dynamic than the orderly universe we once imagined. The wanderers are out there, moving through darkness, carrying their histories, waiting to be found, and we're finally ready to see them. The next decade will change everything we think we know about these invisible wanderers. Roman launches in 2027. Gaia releases its lensing catalog in 2025. Gravitational wave detectors are getting upgrades that will triple their sensitivity. We're about to go from finding one rogue black hole every few years to detecting dozens, maybe hundreds annually. And here's what that means practically. We'll finally be able to test our theories about how common these objects really are. Right now, we estimate 100 million stellar mass black holes in the Milky Way based on models of stellar evolution and supernova rates. But models can be wrong. They've been wrong before. When we actually start counting rogues systematically, we might find there are twice as many as predicted. Or half as many. Either result would force us to completely rethink how massive stars die and how black holes form. The intermediate mass population is even more uncertain. Theory says hundreds should be wandering the galactic halo. Relics from when the Milky Way absorbed smaller galaxies billions of years ago. But we've found maybe one or two convincing candidates. Are the rest hiding in regions we're not looking? Or are there just fewer of them than theory predicts? Roman's microlensing survey should answer that. It'll monitor enough stars across enough of the galaxy that if intermediate mass wanderers exist in the predicted numbers, we'll find them. And if we don't, that's equally important. It means our understanding of galaxy formation needs serious revision. Then there's the question of what happens when these wanderers finally encounter something. The black hole creating the 200,000 light-year star trail proves that rogues can have dramatic effects on their environments. But is that rare or common? Do most wandering supermassive black holes eventually plow through gas-rich regions and trigger star formation? Or was that one event a cosmic fluke we happened to catch? We're about to find out. Deep sky surveys are already being reanalyzed, searching for similar linear features that might have been overlooked. Each discovery will tell us more about how black holes interact with the intergalactic medium, how they shape the distribution of matter on the largest scales, how they influence cosmic evolution in ways we're only beginning to understand. And all of this connects back to the fundamental question: how dangerous are these things really? The math says we're safe. Probability is on our side. Space is vast. Black holes are rare. The chance of one passing close enough to harm Earth is negligible over human timescales. But negligible isn't zero. And the universe operates on timescales far longer than human civilization. 4 billion years from now, when the Milky Way and Andromeda merge, the dynamics will be chaotic. Billions of stars will have their orbits disrupted. And somewhere in that chaos, rogue black holes will be flying in every direction, kicked by three-body interactions, by close passes with massive objects, by the sheer gravitational violence of two galaxies tearing each other apart. Will Earth still exist? Probably. Will it be habitable? That depends on variables we can't possibly predict 4 billion years in advance. But the rogue black holes wandering through that merger definitely won't help our prospects. What's fascinating is that this has all happened before. The Milky Way has absorbed dozens of smaller galaxies. Each merger created rogues. Some of those ancient wanderers are still out there, moving through the halo, carrying information about galactic conditions billions of years ago. They're cosmic time capsules. If we could study them up close, we'd learn things about the early universe that no other method could reveal. That's probably not going to happen anytime soon. But we can study them from a distance. We can measure their masses, their velocities, their trajectories. We can model backward, figuring out where they came from, when they were ejected, what kind of merger created them. Each rogue tells a story. The asymmetric supernova that kicked it into motion. The galaxies that merged and flung it outward. The billions of years it spent moving through darkness. The near misses with stars and planets. The gravitational dances with other massive objects. And we're finally developing the tools to read those stories. The universe isn't static. It's not peaceful. It's not orderly. It's violent and chaotic and full of objects moving at tremendous speeds through vast empty regions where they'll never be seen. But they're still there. They're still real. They're still shaping the cosmos in fundamental ways. The invisible wanderers are everywhere. In our galaxy. In every galaxy. Moving through intergalactic voids. Creating stars in their wakes. Carrying the memory of ancient violence. Waiting in the darkness. We've spent all of human history looking at the universe through light. Watching what shines. Studying what's visible. But the universe is mostly dark. Most of its mass doesn't emit light. Most of its objects are invisible. Black holes are the ultimate expression of that darkness. Pure gravity with no light. Matter compressed beyond recognition. Space-time warped into shapes that break our intuitions about how reality works. And they're not sitting still. They're moving. Wandering. Exploring the galaxy like cosmic nomads with no destination, no purpose except to exist and to move and to warp everything around them through sheer gravitational presence. That's what we're really discovering. Not just that rogue black holes exist, but that the universe is fundamentally stranger than we thought. More dynamic. More violent. More full of invisible threats and invisible wonders that we're only beginning to detect. The next time you look up at the night sky, remember. Between those stars, invisible things are moving. Objects that could destroy planets with their gravity alone. Wanderers that have traveled for billions of years. Monsters that create stars even as they race through empty space at thousands of kilometers per second. They're out there right now. Moving through the darkness. And we're finally learning to see them.